Welcome everybody to
Joves, if you're here, I don't think we can see or hear you. You're muted and your screen is and your cameras are turned off.
I don't know why when I start recording it just turns off my camera and my sorry about that. So I was saying welcome everybody to office hours. We will be covering graphs today. I don't have any notes or any slides to be covering because we're going over mostly the practice problems that's been assigned to you. But I will cover any questions that you may have about the material. So feel free to ask. The first question a student asked me was to go over how TwoSat works. And I am trying to pull my old notes so that I can find that. Let's see. Do I even have notes on TwoSat? I feel like I did. Let me just double check. So I do. Partial TwoSat. Okay, so I'm going to paste my notes on TwoSat, and then I am going to talk about it. This might deviate from the lectures a little bit. These are my own personal notes on how I learned about TwoSat. Okay, so the idea of TwoSat is that you take a CNF and you encode it into a graph such that they are related, and then you run DFS to find information about that graph, which ultimately helps you find information about the TwoSat itself. So CNF is a very common computer science problem, satisfiability problems. For anything more than two, so like a 3-sat or 4-sat or most sat problems, it is NP complete. However, for 2-sat, it is in the we have a polynomial time solution for it. The number 2 means how many literals is maximum literals is in each clause, and so a 2-sat can only have up to 2 literals per clause. Okay. So your initial input is a Boolean formula in CNF form, such that each clause contains at most 2 literals. Okay. The formula is backed by a list of n variables representing at most 2 n literals in n clauses. And what that means is that a literal takes on the form of a or not a, something like that.
You're not showing your screen, by the way, Jovis.
Oh my gosh. It just like reset everything after I hit record, huh? That's kind of.
I think what ends up happening is because you have to agree to have your voice or video, it resets everything, so in case someone forgot to turn it off if they don't consent to being seen or something.
Okay, that's right. Okay, so your literals are a and not a, and then your variables are the variable a. So the variable a can be set to true or false, and you can look at it. There's different ways of like talking about this. Either you take the variable and you set it true or false, or you take the variable and you have 2 literals representing it, a and not a. Both ways work. Just be aware of what it means when someone talks about CNFs like that. So we take these literals, and then we have basically a state of like the output is whether these literals are assigned or to true or false. And the thing is, you can assign not a to true, which sets not a as a assignment to true, and you can set a to false, which means don't set it. It is confusing, but you'll get used to it. And a and not a cannot both be true or both be false. They have to be one true and one false always. So that's how CNF works. Look it up on Wikipedia if that's you don't quite understand. That's considered material you should have known before coming to this class. Okay, so you have each variable which assigns two two literals. Okay, so then we take that. The two-set program takes that two-set CNF into a graph and solves it. Okay, so first you create a graph G from F by mapping the CNF to two n vertices, so one for each literal and two n edges for each implication. So let me go and find what the, because I'm sure there's graphics in the video that I can use. Let's see. Satisfiability. Yep. Two set. Does it show a graph of this? Okay, doesn't show a graph, unfortunately. Okay, so you basically create a graph that transforms to two set. So if you had like a two set, like let's say A or B, and not A or B, something simple like that. Create a graph by mapping the CNF to two n vertices, so one for each vertex. So we have A vertex, a B vertex, a not A vertex, and a B vertex. But not B vertex. Okay, so those are representations. And then we create edges. Okay. Well, I have not covered this in a long time. I'm trying to remember what happens here. I'm gonna have to rewatch these lectures to go over this. I was not prepared to cover two set. I'm sorry.
Sorry,
Give me like
Joves. My bad.
it's okay. Like if I had prepared for this, I probably would have been able to better do this. But I will do this hopefully the next time we have class. I'll try to remember this. Let me see. Was it
Thank
in
you.
the? It's okay. Sorry about that. Um, I forget how like it converts to a graph, which is the part I'm missing. But basically, once you convert it to a graph, it runs an SEC algorithm, and then it looks for pathing, right? So like if it considers whether you can path through the variables in such a way that there's no conflicts and no contradictions, and if there is, then you can assign them various things, and your SECs are just like assigned to be false or assigned to true, and then everything in between just kind of works out. So I will uh, get this sorted out, and then we can cover this next time. Sorry about that. Let me take a look at the practice problems that you were assigned, though. This homework 5, practice problems.
May I ask a question, please?
Yes.
So will you be able to have a small, let's say, half an hour or something, revising the algorithms that we may use in our problems? Because I think a lot of things were not covered by the lectures, and we need to have them in our mind for the homeworks or the exam. Maybe next time
There
also
should
when talking
there
about two
should be
sets, we
a
can. Yeah.
there should be a post on all the algorithms that you're allowed to use for this class. Is that
Yeah,
what you
I
mean?
saw it. I read it, of course, but it's like something like a lot of things in one post, which is more than what I can remember or really understand in details.
Um, So I mean, I don't think you have to try to like learn the entire post all at once, but you do have to know the material in that post. So some of the algorithms are going to be the ones that's covered in class. So like, I believe the DFS, topological sort, strong SEC algorithm are covered in class. There are some algorithms in there that are considered material that you should have known coming into class, which is like the BFS, Dijkstra's, and then I think we also have Bellman-Ford and Floyd-Warshall. Skull Script. So you have like several weeks. I wouldn't try to like go in there, read the entire post, and just like decide, oh, I need to know everything that's in this post. Like break it up into follow along with it in the lectures. But those are the topics that you need to learn.
Okay, thank you.
Yeah. But if you have like a specific question, I'll try my best to answer it as well once I prepare for it. But like I don't there's not really anything I can be like, oh yeah, you should definitely
Yeah, so I was thinking about something like the DP, where you said, for example, if you see the exercise like that, you should think about, for example, using knapsack problem, or you should think about using windowing. So is there something similar here, or
Yeah,
no?
I covered that last week. I went over the basic strategies of using the different algorithms and how you should consider them. And my key, big takeaway was when you first see the graph, or when you set up the graph, write down all the different graph properties that you have. And
Okay.
then if those graph properties are saying, oh, this is a directed graph, then you know that there are certain things that certain algorithms that you're just not going to care about. You're not going to care about Kruskal's or prims on a graph that's directed. On a graph that's unweighted, you're not going to care about MSTs. On a graph that's unweighted, you're not going to want to run dice rows, right? So like that's how you properly identify which kind of graphs, and that's all in the black boxes on like oh, this black box works on this type of graph. So if you don't have that type of graph, you don't even really have to consider that algorithm.
Okay. Thank you very much. I missed
Yep.
your lecture last week, so I will
Well, yeah.
try to
So I
find
definitely
details.
covered it last week. Yep.
Yeah. I'm sorry. So sorry for the question. I thought this is the first lecture on the. Okay,
Nope.
thank you very much.
Yep. Okay. So let's try to cover some of the practice problems. Yeah, go from there. So let's see. This is 3.3. I think 3.3, yeah, 3.3 is just going to have you walk through it. You have the solutions in front of you, but I'll try to walk through it live so that we can kind of get an understanding of what to do. Okay. All right, so here's the solution that's provided. So the first question, so it says, whenever you have a choice of vertices to explore, always pick the one that is alphabetically first. So when you, be careful here, because when you run a black box, you can't indicate something like that. You have to assume that your DFS is sort of, just going to pick any vertex that it comes across. But in this case, just for the sake of walking through a DFS run, we're saying, okay, well, if you have two letters that are equal, then we'll just do that. So what does DFS do? DFS takes your first index and it tries to go through as far as it can before it starts backing up, right? And because we want to do pre and post numbers, whenever we enter a vertex, we indicate what number that is as a pre number. So when you enter it the first time, that's the pre number. Yeah. When you come out of it, when you say, okay, I'm done exploring this vertex, when you leave it, that is your post number. Okay. So the way it works is that right now we can either start with A or B, but because we are specifically looking for alphabetically first, we're going to go with A. So here we have a 1. Okay, I will try. Oops. I will try to indicate my numbers in 1. Okay, so I entered A. My next vertex that I can get to is C, so that's a 2. And then I can either get to D or E, but because I'm going to pick alphabetically, I'm going to go with D. So this is 3. And then you don't jump to E. You continue the depth until you can't go any further, right? So the next one is actually F. And then we finish off at G, which is 5. Okay. 5 has no vertex that follows it, so it's a sync vertex. And so at that point, we can put our post number into it immediately. So the post number here is 6. We go back to F. F has a second vertex that it can visit, right? So we go to H, and H is now 7. Now remember, the pre-number and the post number is using the same counter, right? So it doesn't reset. It doesn't go to 1, 2, 3, 4, 5, and then 6 on the next prenum. It is a single counter that's used for both prenum and postnum. So you go 1, 2, 3, 4, 5, then your 6 is a postnum, and then you go to 7. Now H is a sync, so it has no vertex to go to. So this is done. This comes back to 8, which then we go back to F, and F is done. So F is now 9. We go back to D. D is done. So this is now 10. Okay. We get to C, right? When we get to C, we have one more vertex that we can visit, which is E. So this is 11. 11, we'll try to visit F, but since F is already explored, it's already visited, we stop. And since F is already visited and there's no other vertex for E to visit, then that also ends. And so its post number is now 12. Okay. And now we go back to C. C's post number is 13. We go back to A. A is done, so that's 14. And then we're done with that entire tree. We're done with the A, everything that A can reach. We go to the next one, which is B. B is 15, right? Yep. And then because 15 tries to visit C, C is already visited, so it doesn't go any further. It doesn't have any other vertex for it to visit. So this is then 16. Hopefully that matches the solution. 1, 14, 15, 16, 2, 13, 3, 10, 11, 12, 4, 9, 5, 6. Oh, yep. So that looks good. All right. Any questions about how prenum and postnum work for DFS? No? Good job. Okay. B, indicate what are the sources and sinks of the graph. Well, a source is any vertex that has no incoming edges. Now, when we look at this graph, it's really easy for us to say that A has no incoming edges. It's a little bit more complicated to do that in an algorithm because, A by itself doesn't know who has edges pointing at it, right? But for now, we can say, okay, A, just visually, it's easier for us to say, okay, A is a source, B is a source, right? And then for sinks, we also say, okay, well, G has no outgoing edges, H has no outgoing edges, so these are sinks, okay? Now, when you actually go and do this with an algorithm, you know that if this was a DAG, you could topologically sort them, and they would just be, the first one would be a source and the last one would be a sink. But that still doesn't tell you where all the sources are and where all the sinks are. The correct way to do this is to say, we identify all sinks by looking at the adjacency list of all the vertices. And for all vertices that doesn't have a outgoing edge, we know that to be a sink. Okay. Now, sources are a little bit harder. So there's two ways that you can identify all your sources. You can either say, we keep track of every single every single edge in the adjacency list, and we just keep like a Boolean array, right? We take a Boolean array of all your vertices, and you set them all to false. Sorry. You set them all to true, because you're looking for sources. You set them all to true. And then as you go down your adjacency list, anytime a vertex shows up in your adjacency list, you mark it to false, because that means that there's an incoming edge to that vertex, and that vertex cannot be a source, right? So that's, you can say it that way. It's a little bit more complicated. The way I like to do it is, the sink is really easy to identify. Find all the vertices with no outgoing edges. The sources have a longer summary, but the other way you can do it is, I'm just going to reverse the graph. It takes all of M to reverse the graph, and it would have taken all of it would have taken all of M to identify all your sources anyways. So take the O of m to reverse the graph, O of n plus m if you want to, O of n plus m to reverse the graph, and then find all your sinks again. The sinks in your reverse graph are the sources of your original graph. So you can do it just that way. Just say reverse the graph, find all the sinks. These are my sources in the original graph, O of n plus m. Done, right? Okay. And one sink, because right here there's two sources and there's two sinks. There's at least one whenever it's a DAG. But yeah, it's not guaranteed to only have one. Okay. Mahmoud?
Yeah, maybe this is a bit of a dumb question, but I know when we run DFS, we're also given a prev, like a prev list, which
Yep.
is telling you what if there's a previous or not. So wouldn't all the sources have nil for their previous?
No, not necessarily, because it depends on when you run your DFS, right? If I was to run my DFS from, because like you look at the graph, right? Like you look at the graph visually and you go, obviously I'm just going to run my DFS from A, and then anything that doesn't have a prev is a source, because you can visually see it. Now, if I gave you a unknown graph that's like a 1,000 vertices, right? There's no way to like visually see that. So you run DFS from some vertex. Now, what happens if I ran DFS from, say, C? If I ran it from C, right? A, B, and C are all gonna have no pre item. So now you can say, oh wait, so C is a source when it's not true. Now you can also run it from D, right? And if you ran it from D, D doesn't have a previous. Now, if C happens to run after A and B, then C will have a pre. But if DFS randomly chose C to be the next node, and then B is not going to pre, and then you end up with 4 sources. I can run DFS in such a way that every single one of your vertices ends up, well, not everyone, but almost all of them end up looking like sources when they're really not. So that's not a way to do it. Does
Okay,
that
so
make
then,
sense?
yeah, that
Yeah.
makes sense. But then a follow-up question. If we run topological sort on a DAG, right?
Yes.
We get the prev list from that topological sort when they run DFS. Is that still also something that we shouldn't rely on?
No, because this is a DAG, right? We're
Yeah.
looking at a DAG right now. And I just showed you, if I randomly ran it from a C, the DFS, you're going to get a topological sort, but C is going to not have a pre. And then you're going to think that C is a source when it's not.
I think I get it.
Yeah.
I'll watch this back, and if I have any questions, I'll.
Yeah, like you don't know enough about, like, if it's a chicken and egg problem, right? You're trying to run DFS to give you information about your sources and sinks. But the only way to know where to run that correctly is to know where the sources and sinks are to begin with. Like you can only do that approach if you run it from a source. But you have to find the source first in order to run it. So like it doesn't work. It ends up not working because DFS can just pick a random vertex to start from.
So then, actually, no, I've taken too much time. I'll ask the question on Ed. Sorry.
Okay. Yep. Brianna?
Okay, so a little bit of summarizing what you said. The only thing that we can guarantee, no matter where the source or where DFS starts to run from, the only thing we can guarantee is that things won't have outgoing edges, and that's a way to identify them. But to identify sources, a approach that you follow is reverse the graph and identify those new things, which in reality are sources, right? And because they don't have outgoing edges, you have now identified things and sources. Is that what you were saying?
Yes. Yes, absolutely.
And sorry, follow up. And reversing that graph, is it OM like you said, or is it ONM? Should I consider an M plus, sorry, N plus M?
You should consider O of n plus m, because even though you're reversing edges, the only way to reverse edges is to traverse the entire adjacency list. And then if you have any vertex that's like doesn't have any edges, you end up paying the cost to visit that vertex anyways. So it's O of n
Okay.
plus m to reverse graph. Now, a student asked if I did the Boolean array approach, what's the runtime for that? It's also all n plus m. So you don't lose any runtime by doing the reverse. It's it's going to be 2 times n plus m versus n plus m, which is the same runtime, and it's fine. And I just think it's easier to understand, like, oh, I'm just going to reverse the graph, find its sinks, and that's my sources. And my sinks are just any edges that doesn't have outgoing edges.
Okay, thank you.
Yep. You can feel free to do the Boolean if you want. It's just I just find it harder to write out. All right. Magenta.
Hey, hi, Joves.
Yeah.
A question about if you use a topos then all the sinks are supposed to be at the beginning of the list and then all the sources at the end, because, sorry, maybe.
Hold on. Sorry, I'm gonna hold on. Before you finish, I just saw in chat. Keep in mind that any directional graph has at least one source, one sink and one source, and that is not true. So students are thumbs upping that is not true, and I can show you why. So I want to address that before I answer the question in case this comes up. If I have a direct graph that's doing this, there is no source because every single vertex has a incoming edge. There's no sink because every vertex has an outgoing edge. But this graph is very much directional. Now, if your question, yeah, only a DAG is guaranteed to have one source and one sink. Okay, good.
Right. Yeah.
All right. Sorry.
Yeah. In the case of DAG, for instance, can we use a property to simplify searching sources or sinks, or it's not really worthwhile to do that?
Can you use what? Sorry, can you ask that question again?
The property of the sources at the beginning and the sinks at the end because of the tuple sorting, like the nodes with.
Yeah, like if your problem just needs one source or like if your solution just needs to find a source or a sink, then you can just use the first source and the first sink and just declare that after a tuple sort. That's fine. That's allowed. But if you want to find all the sources and all the sinks, you have to give details on how to do that.
Understood. Thank you.
Yep. All right. Moving on to the next problem. What is the topological ordering is found by this algorithm? Okay. Well, we topologically sort by the post numbers in decreasing order, right? Yes. So if I take a look at, I'm going to use this right here because it's kind of written out. This is a little bit harder to read up here, so I'm going to use this. Okay, so if we take the highest number, which is 16, so this should be first, 16 and then 14. So let's see, 1, 2, 3, 4, 5, 6, 7, 8. So it should be B, A, C, E, D, F, H, G. Yep. So that's your topological sorting, and that's how you do it. You just take the decreasing. You take your numbers from decreasing order, right? Yeah. And so what that ends up looking like is saying that for B and A, right? The thing about topological sorts is that B and A can actually be flipped, right? So like depending on how DFS was to run, like this specific problem to make things easy said that you do it alphabetically, but B and A can be swapped because B and A aren't dependent on each other. So it could have been AB or BA, doesn't matter. C has to come after those because both B and A point to it. That's fine. E and D can be swapped, but they both come after C and they both come before F. And then H and G can also be swapped. Okay, and so that's the like how topological sort is saying is that every vertex to the left, going from left to right, a vertex on the right of another vertex cannot have an edge going backwards. It can have no edges going forward or an edge going forward, but there is no way for they can't have an edge going backwards. So B and A both point at C, so it's pointing forward. That's fine. B and A doesn't point at each other, so that's also fine. How many topological orderings does this graph have? Okay, so I already said that we could pair these up a little bit. B and A can be swapped. E and D can be swapped. H and G can be swapped. So you end up with 2, times 1, because C cannot be swapped, times 2 times 1 times 2. And that equals 8. So here should be it. Yep. So the answer is 8. You have 8 different ways to swap it because those 3 of the pairs can be swapped interchangeably. Okay. Any questions about oh, we have hands. Okay, yes. Mahmoud?
Yeah, sorry. I might have to go back a little bit because I asked the question in chat, but I don't think you saw it.
Okay.
You said that the way to find the sinks would be to do like a Boolean array and see if there's anything that, like if there's an outgoing edge, and if there is, you put it as false. If there isn't, you put it as true. But
So
we're
not on the sinks. On the sinks, it's easy. On the sinks, you could just read like your adjacency list, right? It's going to look. This is not going to. Well, I guess we can do it this way, right? So if we look at the graph here, your adjacency list looks like this. Okay. So notice how G and E doesn't have any outgoing edges, so they just immediately sinks. So to find all your sinks on a given graph, what do you guys think the runtime is for this?
O of n.
Yes. So this is O of n. Okay. You don't have to check every edge. You just have to check every vertex. So it's O of n, and you can identify your sinks. Now, if I wanted to check all my sources using a Boolean array, right? If I want to know if A is a source, I have to check to see if B contains A, if C contains A, if D contains A, E contains A, F, and so forth and so forth. Then I say, okay, no, A is not. Nothing points at A, so A is a source. Same thing I do with B, then C, then D, then E, then F, and then G. And that actually ends up being a bad runtime because I reset my information whenever I go to each and every vertex, right? So if I was to check C, I will check all the other vertices. If I was to check D, I would check all the other vertices. So if you wanted to use a Boolean array, you just say, okay, well, I'm going to set this up, with all my letters, and then if nothing points at A, I leave it alone. If nothing points at B, I leave it alone. If something points at C, I set it to false. If something points at D, I set it to false. And then you just go through all your your vertices and your edges one time. So that's all of n plus m. Or you can reverse the graph and then do the same thing to check for sinks, and that's all of it.
Okay, I misunderstood. I thought we were doing something like altering the black box. That's why my confusion happened. Sorry.
No. This is like completely like outside of. You don't do it within DFS. You just do it outside of it.
Okay, thank you.
Yep. Tejas? Tejas?
Hey, Joves, can you hear me?
Yes.
Yeah, thank you. My question is around D. Like, how is there a general rule or a pattern we can follow so as to identify how many topological orderings exist for any graph? Like for this was pretty symmetric, so you had choices. But what if it does not look symmetric and it's a very much messy one? So, are there any general rules? You can do it in some better way.
I actually think identifying all topological orderings is actually a really hard problem.
So
So it's
just as an
exponential.
example,
So yeah, it's an NPC. It's a NP complete or NP hard problem. It is finding a single topological sort is really easy. Finding all of them is very hard. So that wouldn't be like a question we'd ask you. This is just to identify if it's easy, but like that's not something you would be asked to do. Not in this, not on this topic. It's a hard problem to solve.
okay. Actually, I got this because there was one in lecture also, and I was not able to figure out how there existed three, but the three was the correct answer.
Yeah.
So Mahmoud has posted that graph. This is
right. So
exactly
like,
the other example.
you basically find all the cases where the the ordering of a section of your vertices don't matter. It's actually just it becomes a really hard problem. So I wouldn't worry about trying to solve that problem. Like this is just like an exercise of like, oh, if you were able to see a very simple graph, like understanding why graphs can have different topological sorts, I think is different topological orderings, I think is important. Finding an algorithm that finds all of them is beyond the scope of this class. Okay. Brianna?
Okay, so
Oh,
I'm sorry, just to clarify. So are you saying that even asking that how many topological orders exist is something we should not expect in the quizzes or exam?
you should
Like, is it also out
understand.
of the scope?
You should understand that a single DAG can have multiple topological orderings, and why
Hmm.
that is, and what that can look like. You would not be asked write an algorithm to find all topological orderings of a DAG.
Okay, okay, I get it. But the count
Yep.
is still something is in the scope. We should be able to know how many orderings might exist.
It turns out the problem is NP-hard. So in order to verify that there's X number of orderings, you have to find X number of orderings. So if I can't ask you to find X number of orderings, I also can't ask you to tell me how many number of orderings there are.
Okay, that makes sense. Thank you so much,
Yep.
Joves.
And you will find this in the next topic after graphs, which is when we follow NP complete, that some problems are just really hard to solve, and most of the time people don't solve them. Okay, Brianna?
Okay, I have two questions. First one is
Yep.
about the A, pre and post numbers, and how, sorry, about finding sources and things. So I understood, and I think I will go with that approach of when you have the meta graph or the example we're seeing right here, finding sinks and then reversing, finding the other sinks, so you identify both sources and sinks. But I think that will be O and M, because at the end you are reversing the graph, right? But
It's
you
all of N plus
mentioned,
M.
yes, sorry, N plus M, yes. But you explained here on the red example that you wrote down, why the need of reversing the graph to find things instead of trying to identify A as a source by checking if there are someone else pointing at A. My question is, if we do that, although I understand it's not a good approach, wouldn't that also be ON plus M and pretty much the same as finding things, reversing, and finding the other two things?
Yep. Yep. That'd
So
be the
even
same
if,
runtime.
okay, okay,
I am not giving you a better solution because it's faster. I'm
okay,
giving you a easier solution to write down. I would
yes,
never propose to you two different solutions where one is definitely more efficient than other. Like there would be no reason for me to tell you the less efficient answer.
yes,
So they have the same efficiency. They're both O of N plus M. Pick the one you're more comfortable writing, because if it comes up and you have to find all sources and sinks, that is not a black box you have access to. You have to explain to us how you get the sources and sinks. So
okay,
just
got
pick
it.
one.
Makes
Yep.
sense. And I think the first option makes more sense to me. And the second question I
Yep.
have, it's about the topological numbers, topological order numbers. What are they trying to reflect? It's just like a way for us to show you how a graph or a DAG goes from in a single direction, all edges, sorry, all edges to a single direction. Is that the main purpose? Because you explained it, but I think I lost it. Can you hear me?
Hello? Can you guys hear me?
I can hear you now.
Okay, I think I got disconnected. Let me make sure the recording is still going. Okay, sorry about that. Sorry, what was your question? I got cut out like halfway through.
It's okay. So topological ordering, what's the purpose of it in reality? Like, is it just to show us how a DAG goes in a single direction? Because I
Yeah,
think
I mean,
you explained it, but I think I got lost.
so a topological ordering is on a DAG, is interesting to us because it means that every single vertex cannot reach any of the vertices that was listed before it. Like that's the rule.
Okay.
And if you're trying to find like a pathing problem, like which vertices can reach E, right? I know right away all the vertices that are topologically sorted before E can't reach it. So that's A, B, and C. Now I can say that F, G, and H. Sorry. If I wanted to know all the vertices that D can reach, I can say every single thing that's topologically sorted before D cannot be reached. Everything that's sorted after D could be reached. And that, in situations, that could make your search space of like, oh, what vertices can D reach smaller. It's there's also like other interesting uses of it. Most of it comes from the fact that you get a DAG after you do the SCC algorithm. SCC algorithm is really good at getting you pathing information in the form of a DAG. So like, I might have hundreds of vertices, and if I wanted to know if hundreds of vertices can reach D, well, one way to do it is to do a SCC, which gives me a metagraph, which gives me more information than trying to figure out if every single vertex D can reach all the other vertices can reach D, because you basically collapse them into one single vertex that represents that entire cycle.
Okay, in a way, it's like an efficient way to finding the parent of a vertex. Because I know DFS gives you the brief list, and you could find parent of a node, but it pretty much depends on the vertex you started, and it goes through that. But is it like this topological ordering an efficient way to find the parent of any node?
It's not efficient. I mean, it's a topological sort is just an part of running DFS. It's just there. It's information.
Okay.
So like one thing I can say is like so what can I do with this topological sort? Like if I didn't have any information about the graph, let me see, where's our topological sort? Right here. Okay. Information that I can say something. If you ask me what the parent of D is, I can say D could be like without looking at this graph. Let's cut that off. D could potentially be a source. That's one thing that it could be. D could potentially be a sink. D could potentially have parents. What are D's parents? Well, D's parents could be B, A, C, or E. It cannot be F, cannot be H, cannot be G. Okay. I know that B is a source vertex. That's one thing I also know. I know that G is a sink vertex. That's another thing that I get from this. And if I wanted to say anything else, is that if there is a single path through from B to G, such that I can get there's an edge from B to A, an edge from A to C, an edge from C to E, and so forth and so forth. I know that there is a single path that can visit all vertices without backtracking. That's another question I can answer given the topological sort. So you get information from it by knowing how they are related to each other.
Okay, thank you very much.
Yep, no problem. Manjunath?
Hey, Joves. Again, the question about the topological ordering. So when we say we swap the nodes, are we still sticking with the question requirement of exploring in alphabetical order? Or the order becomes like starting from B, A, C here, and then the next one will be A, B, C, so on.
Which part of you asking a question on?
The topological ordering that we are talking about.
How many there are? So DFS, right? Let's pretend that DFS is written in you wrote DFS, right? Your implementation of DFS is always going to give you the same topological sorting, I would think. Like you're not going to write a random, like between B and A, pick something random. You're going to have a set way of picking between B and A. Either you pick the first one that you see, or you pick it alphabetically. You do something, and because you do something, when I hand you the same input, I'm expecting the same output, right? It's called a staple algorithm. Like the algorithm with the same input will give me a same output that's valid. Okay. My implementation of DFS might give a different output. but it'll give the same different output every single time that I run it. So what this is saying is that given how we make a decision on which vertex to pick, what is the topological ordering that would be outputted by this approach? However, this graph has multiple topological orderings. My implementation could do it one way. Your implementation could do it another way. What are all the different ways that this graph could have been topologically sorted is what the question is. So it's no longer caring about the alphabeticalness of it. I'm just using the graph and calculating how many possible topological orderings there are. And for this problem, it's easy because you can visually look at it and it's easy to say, oh, there's 8. But in for an n number of vertices is actually a very difficult problem to solve. That makes sense?
And that makes sense. But the last part is the number of, in this particular example, it is easy to figure that out. Like there are 8 combinations. And again, the question was a little ambiguous on whether it is a number of vertices or it's always starting from the source to sink. That kind of ambiguity I got into when I was solving this.
The question is asking how many topological orderings are there? The definition of topological orderings is defined. It's sorting from your source to your sink with all vertices to the left of a vertex not coming after that vertex, right? So like the vertex on the right cannot have an edge to a vertex on the left. That is the definition of topological ordering. And then the question is, how many ways can we order this graph topologically? And that's it. I don't think there's like any additional gotchas out of that.
I see. Okay, thanks.
Okay. I'm going to answer 2 more questions, and then I would like to move on to the next question. So, Linfen?
So can you scroll up a little bit for the ON time complexity, how you get the sync? So you also go through all the vertices and also the edges, right? So otherwise you won't be able to know the direction. Why you all think this time complexity is ON? And second question is, I think the simple way is look at for source or sink, just look at whether they have outgoing or in, just have like in going edges, then we can decide, right? We don't need to think about that complicated.
So the first question, why is it O of n? Because I don't have to look at any of the actual edges to know whether I have outgoing edges or not. I just need to know if there's an outgoing edge. The second I have a single outgoing edge, it is immediately not a sink anymore. So I don't have to go through. So like if I was looking at the vertex C, I don't have to see that there's 2 edges coming out of it. I just need to know if there's a edge coming out of it. So it's all of 1 on each vertex to find out if it's a sink or not. And then if I do it on n vertices, it's O of n to find all the sinks, right?
Yeah, okay.
Like, okay, so that's O of n. And the other question is, why can't I just look at incoming edges? In an adjacency list, A has no idea all the edges that's pointing at it. It does not have a data structure of incoming edges. Adjacency list is a list of vertices and all the edges coming out of that vertex. So for A to know if there's any incoming edges, it has to check every vertex to see if it has incoming edges. For B to know if there's incoming edges, it has to look at all the other vertices. Not just the vertices, but all the edges of all the other vertices. That's why you can't just simply say, oh, it has no incoming edges.
Okay, thank you.
Yep. All right, Nicholas, you get the last question on this problem.
Cool, thanks. So on Wednesday's office hours, there was talk about topological sorting lends itself to dynamic programming problems. I'm assuming if we use like this graph as an example and we wanted to see the information as it flows through, we would reverse the graph like we've talked about. Then we could look at the adjacency list, and for each of them, so O of n times, we can look at whatever the previous one is on that reversed graph, similar to trying to solve a sink, but instead of, canceling out the m because we're just checking if it's populated or not, it would be O of n times m then.
It depends on the problem. I don't
Okay.
really, I can't give you a runtime, like just a general runtime of all dynamic programming problems that
Yeah,
would represent this. Yeah, and that's a good point. That like a topological sort is actually a very good information to have for a dynamic programming type approach to a problem. So like if you know for example, if you were to do the security camera problem, right? Each of these arrows could represent the house that each vertex has a view of, right? And if you wanted to know, if I can get away with robbing one house or not, you need to know how these houses see each other and how they line up. So you do the topological sort, and then you do dynamic programming based on that sort, right? Like it would be efficient for D to work when you're robbing house D to worry about F, G, and H on whether it can see it or not, right? So yeah, you can use topological sort to set up a dynamic programming problem. Yep.
all right,
Right.
thanks.
Yep. Let's see. The next problem is, did I answer all of that? I did. Okay, 3.14. No, sorry, 3.4. Can I catch all this? I think so. Okay. So 3.4 is run the strongly connected components algorithm on the following directed graph G. When doing DFS on G reverse, whenever there's a choice of vertices to explore, always pick the one that is alphabetically first. Okay. In each case, answer the following questions. In what order are the strongly connected components SECs found? Which are source SECs? Okay, so I'm going to post the solution, and then we are going to walk through it. Oh, do we have two graphs? Oh, we have two graphs. Okay. All right. Let's try not to mess this up. By the way, this kind of question is really good in terms of like walking through so that you have an understanding of how these algorithms work. And it is really easy to make a mistake on these. Don't worry about that. You're not going to get a problem on the exam that's going to be like, here's a graph, do a DFS on it. Here's a graph, do an SCC on it. That would be like, it takes such a long time. It's uninteresting and it's error prone, and you're probably going to get it wrong. Just like I'm probably going to make a mistake, as I did with the first problem. The point of this is to understand what these black boxes are doing so that you have a better understanding of how the solution, how the output relates to the input and stuff like that. Okay, so all right, so first we run so we run DFS so that we get all the we get to know where all the vertices are pointing at each other, and then we are going to reverse the graphs, right? So probably only going to do it on one, and you guys can work on the other one. I don't want to sit here doing this all night, all day. All right. All right. So that is our graph reversal on just the green edges. Okay. Now we run DFS again on the original sync SECs. They end up being discovered as our they end up being discovered first. So anything that's like at the end of our SEC run or is the first thing that gets discovered because it removes it as a going reverse. So let's see. Where would we have started? Assuming we would have started at A, right? we would have come over here. We would have found that this right here is an SEC, right? Because it would have reverse. Sorry, this would have had the post numbers, the smallest post numbers, and so it would be done in reverse because it would do the largest post numbers first. So because A points to this, and this ends up being the first round of vertices that would have assigned its post numbers, it would be discovered as the first SEC. Is that right? C, D, F, J. Cool. Okay, so then after that, we would go to H, which is right here. This is also an SEC, so this would have been discovered next. So G, H, and I. Yep. And then it would have come back to E. E would have had nowhere to go, so it would have discovered this as an SEC. And then A would have been done, so A would have been discovered as SEC, and then B would be the last one to be visited. So that's SEC. So this is 1, 2, 3, 4, 5. Let me take a look at my notes to make sure I agree with this answer. It's 3.4, right?
I think you might have flipped A and E, because if they're ordered by descending post numbers, A would have a higher one than E, and then B.
Oh, yeah,
So
yeah, that's right.
I think
Right,
you
right.
might have flipped them.
Okay. You are correct. So this is 3. Yeah. And it turns out that when I did this, I actually did all the numbering. So that's kind of helpful. So this isn't part of the model solution, but that's what I did. So normally we don't need the details of an algorithm because we're doing black boxes, but since we're doing it by hand, we need to know how to run the SEC algorithm. So we first reverse the graph, visualize this since I'm not going to redraw it. And then you run the DFS with pre-post numbering on the reverse. Then we run DFS with CC_num on G with the vertices sorted from largest post numbers. The order of our source to sink SECs go from highest CC_num to source. So when we run it on the reverse graph, we start with A, right? And then we go to B, which is 2. And then B is done. So we get the 3 here as our post number. We go back to A then goes to E. So E gets 4. Yep. And then E has nowhere to go. So E is done. So it's 5. Then it goes to, is A done after that? A is done after that because A has no additional vertices. So then we go to F because it goes A, B, E, and then, no, we go to C. Yeah, we go to C. Okay, C is here. So C is assigned 7. J should be assigned 8. F is assigned 9. And this is 10. Then 10 has nowhere to go, so this becomes post number of 11. Go back to F, which is can come to H. So H gets 12. Yep. I gets 13. G gets 14. B was already done, so G goes to H. So this is all done. So we retract all of it, getting the post numbers, and then we come back to F and we retract all of it, getting all the post numbers. So this is your pre numbers and your post numbers based on the reverse of the graph. Once we have the reverse of the graph, we are going to say, okay, run DFS with CC_num on G with the vertices sorted from largest post number. So our largest post number is J, which is 19. So this is our, C, which is 20. Yep. So this is CC_num1. So we go from C, and then everything that C can reach, which is J, F, D. Sorry, you use not the reverse, you use the original. So C, D, F, J, and C should all get 1s. So C, D, F, and J all gets 1. Okay, so done. So the next one we do is 2019 is already done. 18 is already done. 17, the next largest one that we haven't visited already is 17, which is H. So we start with 2. Now everything that H can reach, so 2, 2, 2, 2. So H, G, and I are 2s. H, G, and I are 2s. Done. Next highest one, 17, 16, 15, 6. 6 on next. Yep, 6. So that's A. All the ones that A can reach, which is C, has already been explored. So A is done, so it's by itself. B also by itself, and then, oh, sorry, E also by itself, and then finally B by itself. And so the ordering of this. So this is just exactly what the SCC algorithm does. First, we reverse the graph, we run DFS, we get its pre and post numbers. We then take those pre and post. We only care about the post numbers, really. We take the post numbers, we rerun DFS from the highest to the lowest, ordering them by CC num. Every time we have to stop, we start the new CC num. Okay. And that is how you discover all your SCCs using the SCC algorithm. All right. Tejas?
Yes, Joes. It's more like a clarification question. So in such kind of cases, when you are just given a graph, is it always a good thing that you start from the lowest labeled vertex, right? If I'm going alphabetically, we should start from A.
Sorry. Well, your algorithm can't specify something like that. All of this is just to say,
Yes.
there's so many ways to walk through this graph and still get the correct answer. Just for the sake of manually walking through this, do it alphabetically. But that direction will be given to you if it matters. Otherwise, it shouldn't matter. Like if I started from D, I would have different pre and post numbers, but how I identify my SACs would end up being the same. They would be identified maybe in a different order, but they would still be identified correctly.
Okay. Yeah, that makes sense. So even if you start arbitrarily, the order in which we identify this SCCs, it should not change.
The SACs will not change no matter what order you do it in, as long as it's the DFS algorithm.
Okay. Thank you, Jonas.
Yep. But like really the questions of like, which order would the strongly connected components be found isn't really like something you really need to, you would be asked, because like, the DFS is just run however it runs. It doesn't like, it's only interesting because you're walking through it manually. That's it. Okay. So here is for the second graph. Here's my table. Okay, so if we were to reverse, same thing. I'm not going to draw it out, but if I was to reverse all these edges, I would start with A. Actually, you know what? I will draw them out because I think it's hard for me to talk about them without drawing them out. So that's a wacky equation I had to do. Okay, anyway, so if we were to run this now, we start with A, which gives us 1, right? A has a edge to E, so E becomes 2. And then E has, oh my gosh, why is my screen being weird? Okay. E has a edge to B, so B becomes 3. 3 goes back to A, so A is, so B is done. Go back to E. Okay, so I'm just going to circle the number. So we got A, E, B. B goes back to A, but has no other vertices it can visit, so we get to 4. E does the same thing, so E is done. And so here is our, we're done there, right? Now we go from, next one is C. So C is 7. C has no edges to any unvisited vertices, so 8 is done. Next one is D. That starts that way. D goes to G, which gives us 10. G goes to H, which gives us 11. H goes to I, which gives us 12. I goes F, 13. F has no no edges to an unvisited vertex, right? So then we start tracking post numbers. 14, 15, we're backing up. 16, 17, and 18, right? So we once we go all the way down our depth, we can no longer visit anything else. We come back up and start assigning post numbers, right? So then we want to start with our highest post number, which is 18. Assign it a CC number 1 to start, and this is on the original graph. So D points to H, which points to F, which points to I, which also points to H. So we go back to F. F has nothing else to point to, so we go back to H. H also points to G. G points to D, which we already tracked, and then it has no additional. So that is one CC num figured out. We're done there. So the next one that is alphabetical is C. C starts at 2. C can point to F, but F has already been visited, and it cannot point to anything else. So that is another CC num done. So then we go to the next letter is, no, sorry, the next lowest is 6. So we start as A. A points to B, which we assign it as 3, and then B points to E, which we also assign, and E points back at A, which has already been visited, and it points at H, which has already been visited, so we're done. So this is our third CC num. So that is how you use the reverse, followed by the original graph to find all your CC nums. Okay, any questions on this second one? No? Great.
Jovis,
Yeah.
there's a discussion happening in the chat, and
Okay.
it kind of got me curious a bit because I think my understanding might be a little off. One of the people are saying that if we run DFS from a different node, would that make your CC num incorrect? So like instead of starting at A, what if we started at, like, for example, I don't know, I in the first graph? Would
Yeah.
that
So
still
CC num. So the SEC algorithm, all it cares about is identifying all the SECs. The numbers it assigns to these SECs are completely arbitrary and just used to group them together. If you run it from a different vertex, a different SEC will present itself either sooner or later than if you ran it with this exact setup. And so they're not wrong, they're just different. Like you don't get a different. It's not a wrong as a CC num. They're just ordered differently, and that's fine. The topological ordering may also be different, but they will be consistent with the rules of topological ordering, and the SECs might be numbered differently, but they will be consistently the same SECs grouped together.
I think the question here though is there's maybe two parts to the question. Like if you run DFS from say vertex B, right, that would find that would basically create a connected component for a large part of the graph that would not be strongly connected component, right? So I think one of the important things is that you run DFS with the vertices sorted from largest post number to smallest, right? That's kind of an important part of the algo. I think there was a question about, is that kind of modifying DFS if you're specifying that you're running DFS with these vertices sorted in this way, and that's how you choose. Like, is that a modification? And secondly, I think my point was that if you don't run DFS in the order of the sorted post number vertices, you will not get the right answer.
Right. So to get the post numbers to be correctly the way they are, you run DFS on the initial reversal of the graph. That gets you the ordering. And then yes, the second part of that, the second DFS, is important to run that in the right order based on the post number. The first DFS doesn't matter. The first DFS can run from any vertex and it'll still just work. The second thing you said is that a modification of a black box? You're not modifying the SCC algorithm. The SCC algorithm does exactly that. So the SCC algorithm will take care of all this for you. It'll run the initial it'll reverse the graph. It'll run the initial DFS to get the right post numbers. It will reorder it so that you run the second DFS on the original graph from the largest post order number, and then it will correctly output the right SCCs. So there's no modification there. That's just what SCC does. And you should never try to rewrite the SCC algorithm. If you need the SCCs, just say run the SCC algorithm and get this output.
So we'll never have something where we have to say like part 3, like let's say we're not running SCC, we're running some other algorithm, and we say, hey, we want to run DFS with the vertices sorted like this, because that's a modification.
It's also not a modification. You're not going to need it, but it's not a modification of the black box. So think about the 3 different parts that's happening here. Okay, so we have a DFS implementation that we know runs. In this example specifically, it says run DFS alphabetically, right? Like if you have to make a decision, run it alphabetically. When you write a DFS algorithm, like if you were actually to implement a DFS algorithm, in fact, we'll look at the DFS algorithm when the coding problem gets released, because we provide you the black boxes. It's going to read a list, and it's going to run the algorithm somewhat deterministically for that implementation from the beginning of the list to the end of the list, right? So it's going to start from the list, and it's going to try to visit all the vertices that it can see, and then it goes, okay, well, what is the next vertex down this list that hasn't been visited yet? So if A, B, and C, and D, or vertex 1, vertex 2, vertex 3, vertex 4 has been visited, the next thing I'm going to start DFS from, or the explore subroutine from, is vertex 5, right? That ordering, when you give DFS the input, can be manipulated. That is your input to the black box. So if I took all my vertices and I alphabetically sorted it from A to I, and I said, here, DFS, run it from A to I, it's going to run it from A to I. It'll take a different DFS path. I mean, it'll take DFS path, in between, but it'll try to run it from A to I. So it's kind of like, remember how I said, like, when you write a DFS algorithm, you're not just picking random vertices. It has a set way of picking vertices. We may implement it differently, but it does have a set way.
See.
And generally, you can accept that it'll start from the first vertex in the list, going down,
that makes sense.
list
So
order.
that might be part of setting up the problem and setting up your list. Yeah.
Yeah.
Thank you.
Yeah. Yep. So someone said for the first DFS on reverse graph, order doesn't matter. Correct. For the second DFS, order matters. Also correct. But that order is determined by the first DFS. So you don't need to specify the second order, nor should you, because the first DFS is doing just that. Yep. Okay. All right. Moving on to the next part. So I did part A for both. Which are the source SCCs? Which are the sink SCCs? Your source SCCs are going to be listed, I think, at the end here, right? Yeah, so if you take a look here, because in the way SCCs are discovered, remember, are from sink to source. So your source SCCs are going to be, if you take the ordering from when they're discovered, and since sinks are discovered first, so we know immediately that the sinks are going to be this one, and this one. And we know immediately that sources are going to be this one and this one. Now we have to take a look at the actual SECs and decide which one, if there's additional sources and additional sinks. So let's make some meta vertices. So we know that B is a source. Does A have outgoing? A has incoming edges, right? So this one right here, and it has outgoing edges, so it's neither a source nor a sink. Well, E is interest, so we can look at E. E has outgoing edges. Sorry for the like drawing all over the place. Let me try to use a different color. Hopefully that helps. So, right, so that's a source. A is nothing. E has only outgoing edges and no incoming edges, so E is also a source. We say A is nothing, and then G, H, and I has both incoming edges to the SEC and outgoing edges to SEC. So we have two sources and one sink, I think, hopefully. And here, so A, B, and E are one SEC. D, G, D, F, G, H. D, F, G, H. That is another SEC. With I, oops. This is another SEC, and then C is an SEC. Now, we know that A, B, and E are a source, right? So it only has outgoing edges, which makes sense. And then we say D, F, G, and H are sinks because it only has incoming edges, which makes sense. Yep. And then C has both an incoming edge and an outgoing edge, so it is neither. So the green are our sources and the orange are our sinks on both problems. Did I get that right? Let's take a look at what the model solution says. E and B as sources. Yep. C, D, F, and J are sinks. Is a sink. Yep. A, B, and E is the source. And then there's a sink, this one. Yep. So I got that correct because we just take a look at the metagraph. And then it says it wants to collapse the, draw out the metagraph. I'll paste this, but you should be able to identify it looking at these blue colors. And I am being so messy today. I apologize. All right, so A here is a meta vertex. It points into CD and J, which is right, CD, F, and J, which is right here. GHI is also one, and it points to this one. Yep. And then B and E are also connected components. B points to these two. Yep. And E points to these two. Yep. And then for this one, we have A, B, and E, which points to C. Yep. C right here by itself points to this giant one. Yep. And then A, B, and E also points to this one. Notice how here A, B, and E points to this bottom SEC twice, and that's fine. Because if this edge was to point back, then this whole thing would become one SEC. So you'd only care about one of the meta edges out of possibly many. Okay. So that is part C. Then part D says, what is the minimum number of edges you must add to this graph to make it strongly connected? Oh my gosh, is that? All right, let's see. All right, so you only have to look at the metagraph, it turns out, right? You don't actually have to look at the full graph anymore. So because the metagraph, if for whatever reason, this is all a DAG, but the second you create a single edge that causes there to be a cycle, then everything that cycle contains collapses into a single SEC. So I think you're supposed to do this visually. I don't know if there's a program to do this, but let's see. So A points this way. So I think how do we properly so we have to take care of the sources and we take care of the sinks. I think that's the main thing. So if we take the sink and we create one edge here, that will make it no longer a sink, right? You need to eliminate any sinks and you need to eliminate any sources because a single SCC has no source, has only one source and one sink. So you have to collapse them. So if we take the sink and we eliminate it, that's one. And then we take these sources and we eliminate them, then they all collapse into one single SCC. So I think the number of edges you need is equal to the number of sources plus the number of sinks, I think. So that takes care of that one. So that's 3 edges. Hopefully that's good enough. And then here we have one source, one sink. And it turns out you only need one edge to, oh wait, that's not the right one. Sorry. So this is source, this is sink. And turns out if you do this, you collapse that. So I lied. It's not the number of sources plus the number of sinks. It's the number of edges needed to eliminate all sources and sinks. So
I think we can save by connecting the sink to the source.
Yeah,
that way
I
you
think that's
eliminate
actually,
sink and
yeah.
source at the same time.
Yeah, so hold on, let's do this. Let's connect this source to this sink. So that's one. So that eliminates both of these. And then that also eliminates that one. You're right. So yeah, you can save by taking all your sinks and pointing it at the sources. So I think it's 2 edges for the first one edge for the second one. Did I get that right? Let's see, it's here. Yeah, 2 edges. Yeah, 2 edges and 1 edge. Two edges must be added to make the entire graph strongly connected. One from any vertex, this one to B. Yep, and then one from this to E. Yeah. So you take your sources and you point to you take your sinks and you point to your sources, and that creates the loop. Yep. All right. Any questions about part D? Cool. Instead of C, D, F, J to B, can we do B to E? I think so, because once you created that loop, you've basically you've effectively, with this edge right here, you've made this into one giant SEC, and then just by pointing B at that one giant SEC, you've eliminated it. Yeah, so you could do it that way if you want. Mahmoud?
Hi, Joves. Sorry. Another conversation was happening in the chat, and I'm starting to question if I understand. If you run DFS, it's gonna run DFS on the whole graph or just from your starting point onward? Like, I'm struggling
It will
to.
DFS will always run on the entire graph. Once it gets to a point where it cannot go further, so there's, look at the DFS algorithm in the book. There's DFS, which is the parent algorithm, and then there's a recursive call underneath it called the explore subroutine. Explore or go from one vertex until it can't continue anymore, and then DFS will go, okay, well, what's the next vertex that wasn't visited, and run explore from there. So DFS overall will always run on the entire graph.
Okay.
Different
I
from
think,
BFS. Yeah.
Yeah. Okay. That was kind of because I misunderstood. Because like, if you have, for example, a DAG, and you start in the middle of the DAG, for example, you go all the way down, and then once you hit no more and you get, to example, back to the middle, does it just go backwards one more time?
So DFS will never try to process a vertex that's already been visited. And if it runs out of vertices in its path, it'll start from the next visited vertex. So like it doesn't go back to somewhere in the middle. It just starts a subroutine from a different vertex.
Like if you were to make, for example, a DAG, like just draw any random DAG on the screen, and then start in the middle of that DAG.
Yes.
You're gonna go to a point where you'll hit the bottom of the DAG.
Yep.
And then you're just gonna go all the way back up to the starting point where you start in the middle. And then if you can't go down any further, does it just go back to an arbitrary point, or what happens? That's sort of where I'm confused. Like if you start at C, for example.
Yeah, it'll just go to another point. It'll just pick pick the next one that's up. So like it'll try to do B. It'll say, oh, C's already visited. Don't bother. And then it'll do A. It could also do A and then do A to B. And then, yeah. So DFS will always run on the entire graph. Now, how you set it up matters in terms of the SCC algorithm. But if you were just looking for pathing, DFS would just visit every single vertex eventually.
Okay. Yeah, I thought
Yeah,
like if
which
you
is
start in
why
the middle,
the
it just wouldn't go
ordering
backwards.
Right, which is why the ordering matters for the second run of the SEC. You use the first run to figure out the ordering, the second run to figure out the SECs from the ordering.
Understood. Okay, that kind of helps because we were having a conversation and I was under the impression that it wouldn't visit the entire graph,
It will always visit the entire graph.
even if there's like a disconnect in the graph. Like if you have
Yes.
a DAG where, like for example, A points to B and C points to D, but B doesn't point to C.
Yes,
It
it'll
would
run
still
on the
run?
entire graph. Yes.
Okay.
Yep.
Okay.
Um,
Thank you. Sorry.
So, Joe, just to add to it, can we say that each restart of a DFS at a new vertex will eventually try to find a new strongly connected component?
If it is the second run of an SCC algorithm, then every new start, the CC number gets updated by 1, and that is a new SCC that it is exploring. Because it's going from sink to source, when it finishes exploring all the vertices in the sink, it goes up 1, and then it'll explore everything there, and then it'll go up 1 and it'll explore everything there. Yeah.
Okay, yeah. Thank you so much, Jovis.
And the reason why it has explore from sink to source once you have ordered all your vertices is because if you explore from the source, everything is just going to look to the DFS run. It's just going to say, oh, I can reach everything. That gives you no information. You want to run it from the most restrictive of the vertices, the sinks, and say, here's all the vertices I can reach. Therefore, this is one SEC. Then you go to the next one. Here's all the vertices I can reach because all the other ones afterward has already been reached. Here's all the new vertices I can reach. That is one SEC. Then you go backwards up to the source. If you started with the source and it goes, I can see everything, what information could you have gathered from that? Nothing, right? That's why you have to sort it correctly and run it correctly. All right. Any other questions? Cool.
Sorry, Jova. Sorry. I'm sorry.
Yeah.
Again, if we look at the DAG you created, A, B, C, D,
Yeah.
and you start at C, you're going to get, for
Yeah.
example, a pre-post of 1 at C, and then 2, 3 at D, go back to C comes 4, and then at B would be 5, 6, and then A would be 7, 8. But then if you're also looking at the prev list, for example, C doesn't have a previous at first, D has the previous of C, and then if you go to B, does B then become the previous of C, or does C
No.
still not? Because it's already been
No.
visited and there's no link, right?
Right.
Okay. Sorry, that was where my confusion was as well. Okay.
Yep. And it turns out that when you order the post numbers here, so right, so that would be an ordering from the largest post number decreasing, right? So we got 1, 2, 3, 4. Now, what happens if I had started this from A? Well, if I started this from A, my numbers are now 1. Look at that. The ordering doesn't change, right? My post number ordering doesn't change. Okay. Now, what if we started from say B? Erase some things. Where's my eraser? Let's get this out of here. If I started from B, right? Doesn't matter. My post number ordering, still the same. Just for completion's sake, let's do D. And then where do you guys want me to start next? A, B, or C? Doesn't matter. Pick one.
B.
Someone type B? Okay. Still the same, right? It's always going to be ordered in the same way once you do the post number. That's why the first DFS, the ordering does not matter. But once I have the ordering, which I know is from decreasing to increasing, I want to run my DFS the second time around in the correct order. Because if I ran the second DFS from say A, right, my CC number is never going to get updated because I go A, B, C, D. That gives me one CC number and done. But if I go the lowest first, I start with D, right? D, CC number assigned to 1. I'm done, right? Because I can't reach anything else. Now I go to the next highest CC number, which is C. So C, this is already reached. Nothing can C cannot read anything else. So this is 2, this is 3, and this is 4. It'll get assigned a different CC num going from the sink to the source. And because of that, I know I am guaranteed to find all the CC. If I did not do this ordering and I just ran it differently, I would not know which one's a sink. I have to run the second algorithm from the sink to the source. Okay. All right. Let's go to the next problem. Okay. So the next question is, how do we reverse a graph? And this is not something that I think we give you reversal of a graph simply by saying, or maybe not. I always forget what the rules are. We change the rules
In
review
the
semesters.
post, we can say reverse a graph, and it's assumed to be O n plus m.
Cool.
I think.
All right. Yeah. So you can say just reverse the graph and you're done. Now, this isn't something you need to really memorize for the exam, but it is also kind of nice to kind of understand how this would work, how this algorithm plays out. Okay. So we want to reverse a graph G equals VE into another graph GR on the same vertex set, but with all edges reversed. This is ER, so that all your edges are now VU instead of UV. Give a linear time algorithm for computing this, and then give this answer. So understanding that this is O of n plus m, I think is useful, important, and why it is, whether you think this is fast or you think it's slow, this is the correct runtime. It can't be any faster because you have to traverse the entire graph in order to reverse them. And it can be slower, but it shouldn't be, right? So first we initialize an empty graph, G of R in the JSON list form for n vertices where n equals the magnitude of V. Then for each U, we iterate through the neighbors of U. Each U iterate through the neighbors of U for each neighbor V of U in G, add this as a neighbor to V. So we take out our graph, and then we're basically saying, okay, every time we find an edge, add that edge instead to the neighbor, not to itself in the reverse graph, but into the neighbor. So by doing this, is one where the vertices are the same, but their direction to edges are flipped. Let me put this. By adding edge VU instead of UV, so you basically just accomplish that objective, right? Creating new adjacencies of n, going through the original graph with m edges of n plus m, adding each edge is O of 1 because it's a linked list, and then our overall runtime is O of n, which is the initial declaration of the adjacency list, and then O of n plus m to go through all the edges to add those edges back, and so it's O of n plus m, which is will be considered to be linear. Any questions about how to reverse a graph? Great.
We need to understand how to reverse a graph, but when we come to solve any of the questions in the exam, we can just say, oh, reverse the graph
Yes.
based on the guidance that we got.
Yes.
Okay, good. Just to know.
I think we have one final problem. Computopia. Okay. All right. Police department in the city of Computopia has made all streets one way for whatever reason. The mayor contends that there is still a way to drive legally from any intersection in the city to any other intersection, but the opposition is not convinced. A computer program is needed to determine whether the mayor is right. However, the city elections are coming up soon, and there is just enough to run a linear time algorithm. So silly, such a silly way to phrase a question. And also, why would you make all the streets one way before running this algorithm to make sure that it actually works? So we know that we have a graph. Well, you have to create a graph first. So the first thing you do is you create the graph, right? So formulate the graph problem into graph theory and explain why it can indeed be solved in linear time. So the first thing is we have to declare what our graph is. I'll post the answer, but I'm just going to shorthand it and draw it out here. We are going to set all our intersections. Okay. I'm going to E equals one way streets. Okay. Now these streets are one way, so these are directional. Okay. So what do we know about this graph? We know that we have it is directed. Okay. We can assume that it's connected. Okay. And the reason why you can assume it's connected is because the claim is that you can drive between any intersection. If the graph wasn't connected, that wouldn't even be a claim to be made. So we can assume it's connected, but hopefully it doesn't matter. Okay, we're going to assume it's connected. Okay. We're not looking for distance, and we're not being asked about any weights, so it's unweighted. Okay. So what algorithms can we use here? So it's directed, it's connected, unweighted. We don't care about distance. So DFS is a possibility. Okay. It's unweighted, so prims and cruscals are out. It doesn't have any sort of flow, so all the max flow algorithms out. It doesn't have, because it doesn't have weight, Dijkstra's is out. Potentially BFS. Okay, these are just algorithms we can run. Okay, BFS is also a possibility, and then the SCC algorithm is also a possibility. Okay, so these are the only three algorithms we even need to discuss. Everything else just doesn't work on this graph. We're not looking for distance. We could potentially look for connectivity, so BFS is kind of possible, but unlikely. So that leaves us with DFS and SCC, right? Okay. We're looking for reachability. We're looking to see if every single intersection or vertex can reach each other. Now, we could potentially run DFS from every vertex or BFS from every vertex. Bad idea. I already told you that last week that you should not run an algorithm from every vertex. But what we can do is, well, if vertices can reach each other, they would be in the same SCC, right? Because SCC collapses all the information about cycles into one SCC. If your claim is that every single vertex or every single intersection can reach each other, then that means that there's no additional SCCs. There's no like one source, one sink SCC, because every sink wouldn't be able to reach a different source, and then two sources wouldn't be able to reach each other. Two sinks wouldn't be able to reach each other. So the only way you can have this is if you have one single SCC that represents all the cycles and it collapses into one single meta vertex. Okay. And so that is what the model solution suggests. Hopefully you guys read the problem or have your book open. So we represent a city in the problem as a directed graph. Vertices are intersections. E represents one-way streets, so forth. We can solve this problem by running an SCC algorithm and checking if there's a single SCC. We can do this by checking that the returned SCC meta graph has a single vertex, meaning the original graph is a single SCC. Okay, if this is true, then we're good. If it's not, then we return false. The reason this works is because by modeling the original graph as original problem as a graph, able to efficiently solve the problem using the SCC algorithm. In a single SCC, every intersection can reach each other. That is what a SCC means. And then so if there's only one SCC, that means that every single intersection can reach each other. If they're in separate SCCs, then that is not true. Okay, runtime O of n plus m to create the graph, O of n plus m to run the SCC algorithm, and then checking to see if you only have one meta vertex is O of 1, and so your overall runtime is O of n plus m. Any questions about this this first part of the problem? Sato?
Hi, yes, so my question was, why did we assume that the graph was connected?
You don't have to assume it that way. I just did because the problem doesn't really make sense. I mean, it ends up not mattering, right? But it's sort of like properties of the graph I either know or can assume that helps me get rid of algorithms that I don't care about. I guess you shouldn't assume it, but the problem doesn't really make sense unless it's connected. Like if you had a intersection that was unreachable, the answer is immediate, right? If you have any vertex that's unreachable, then the claim is false. So it only makes sense to run this algorithm if there's only one. But yeah, you don't have to make that assumption if you're uncomfortable with it. That's fine.
Okay, thank you. And I think the other question I had, so I didn't had the idea of checking whether the meta graph has only vertices. So instead I checked like the CC num array and then check that all the values in the CC num are the same. Would that be valid?
Yep. As long as you say that runtime is O of n plus, which is dominated by the O of n plus m. Like as long as you get the runtime correct and the answer is correct, you're fine.
Okay, thank you.
The Tira?
Is it always safe to assume that it takes O of n plus n time to create a graph?
If you have to create vertices and you have to create edges, yes, you can assume that it's O of n plus m. Plus, it's just anytime you want to deal with the whole graph, just go with O of n plus m. That's if you're not calculating anything, you're just looking at the whole graph, getting information out of the graph, then O of n plus m. As long as you need both the vertices and the edges.
Thanks.
Yep. Edward?
So in the algorithm section, you mentioned we're going to represent this problem as a directed graph. You don't mention how you make the adjacency list. I think one of the prerequisites for all the black box algos are graphing adjacency list format. Would we get points out, do you think, or do we have to specify that?
We assume that your graph representation is in the adjacency list. You can assume our representation when given the problem is in adjacency list. They're very niche problems that would otherwise use adjacency matrix. If that ever comes up, I'll point it out. But if you don't say anything about how you construct your graph, we assume it's in the adjacency list. Just like you can assume from us it's an adjacency list unless we specify otherwise, which we won't.
Do you think there would be a case where, I mean, sometimes it might matter how you construct the adjacency list for some algorithms, potentially?
It could be. Like you could, like I said, we try not to give those problems where like the ordering of your adjacency list matters in any way. Like we would try really hard not to give a problem like that. And if you're going down that path, you're probably overthinking it.
Okay, thank you.
Sato? All right, moving on to the second part. Suppose it now turns out that Mayer's original claim is false. Imagine making a false claim like that, and then just be like, nah, it's still okay. Okay, we'll continue with this plan that I've already implemented, and there's nothing we can do about it. She next claims something weaker. If you start driving from town hall, navigating one-way streets, then no matter where you reach, there is always a way to drive legally back to the town hall. Formulate this weaker property as a graph problem and carefully show how it too can be checked in linear time. Okay. So then the weaker claim is that everything I can drive to from the town hall can drive back to me, right? And so that claim basically says that the town hall, anything the town hall can drive to is a cycle back to the town hall. So all the places I can drive to must be within a cycle of where I am. There's only one situation where that can happen, right? Because if you only have one SEC, then yes, that's perfect. That's perfectly valid. The second thing is that, okay, well, if your the SEC that you're in has no outgoing edges, because the second you leave your SEC, you can't come back to the SEC. That's what an SEC ends up being. So if your SEC, if you have a road that left the SEC to another SEC, you're never going to come back, because if you could come back, you would be already in the same SEC, right? So that means that the town hall has to be in a sync SEC, which means that the SEC the town hall is in has no outgoing edges. So there's nowhere for it to go that it can never return. So all you have to do is find the SEC metagraph, check the metagraph that the SEC that the town hall is in, the meta vertex that the SEC, the meta vertex that the town hall is in is async SCC. And that's it. Okay. Let's take a look at what the model solution looks like. There is a second way to do this. I know students like to ask about it. I will tell you what the second approach is, which is also perfectly fine. Okay. Algorithm requires modeling the problem, blah, blah, blah. Wait, did I get this right? Yeah, okay. Again, all of n plus m time, we instead check that the town hall is in sync SEC, that is ensuring that there are no edges directed out of the SEC containing the town hall. Do this by examining the SEC that in the DAG that we've already construct by running the SEC algorithm, check that there's no outgoing edges, and then your second weaker claim is true. Okay. The weaker claim requires the town hall resides in the sync SEC. If it lies in the sync SEC, then we know from the town hall we can reach every intersection within S, but we can't reach any other location that can't come back to us. Okay, and so that's why it works. Runtime is to do all of n plus m. SEC algorithm is again all of n plus m. Checking the CC num of town hall is all of 1. Checking that there's no outgoing edges is also all of 1. So your over runtime is all of n plus m. The other way to do this is that if you were to take your town hall and you run BFS on your town hall, and you check every single vertex that that your town hall can reach, and it has the same CC num as your town hall, then that too is correct to make the claim. Basically, it says that every single intersection that the town hall can reach via BFS is in the CC num and therefore creates a cycle with the town hall. So that also works. I prefer this answer because it makes more sense to me. But if you wanted to do it the BFS way, that also works. All right, questions starting with Mahmoud.
Hi, Joves. I still don't understand the solution that you're showing us in front of us. I don't fully comprehend why this works.
Yep.
Can you give us an example or maybe talk me through
Yep.
it?
Yep. Right. So imagine I have a bunch of vertices. Right. Then I have all these edges. Right. And for the sake of argument, this is a single SEC, okay?
Okay.
If I am not a sync SEC, right, then I would have some other bunch of vertices here that's interconnected. If I was able to reach out of this this SEC, the SEC my town hall is in, there's no way back ever, right? There's no way to come back into this SEC, right? Because the moment there's an edge that exists that comes back to this SEC, this would have been declared as a single SEC. Even if there's an intermediate oh crap, hold on. Sorry, I'm on call right now, so I'm gonna finish this up, and then I gotta go deal with a on-call issue. Okay, so even if I had a intermediate vertex, meta vertex like here, right, that I can say, okay, well, this reaches this and this reaches that. This right here would have collapsed into a single SEC, because an SEC basically says all cycles are collapsed into a single meta vertex. So your only situation where I have a vertex that reaches out of it is to another vertex that can never return back to it. And if that's the case, then the claim by the mayor is wrong. That means that from the town hall, I can drive. So let's say, oh, did I not draw out this correct? Yeah, okay. So I would potentially be able to drive this path and never return back to the town hall, right? So the only way for the mayor's claim to be true is if this entire SEC right here was a sink and it doesn't have any outgoing edges, and that's it. That's the only way for that claim to be true.
Yeah, that makes sense. Thank you so much.
Yep, no problem. I'm Sato.
Yeah, so the second solution, I realized that the solution I went for is much more complicated than it should be. But instead of like using BFS, can we still use DFS? So we run DFS and then we check the vertices with the same CC num as the town hall, and we delete all the other vertices. So like we make sure that we only keep the vertices in the graph that are reachable from the town hall, and then we run the SCC to check that all that, like similar to A, to check that all that form only one SCC.
Yeah, that could work.
Great, thank you.
Brianna?
Okay, so you gave a second option of how we can solve the B question, which is run BFS, check the CC num of the vertices that were reachable, and I think that's it. But I'm checking the black box, and BFS doesn't really return the CC num. Does that mean we cannot use it that way, right?
1 second. I got people. Okay. So, I'm so sorry. I'm so sorry. I'm being distracted. Can you ask the end of that question again?
No, it's
I
okay.
apologize.
No, it's okay. You gave a second approach to solve the question B, which is run BFS and then check the CC num, and if all the nodes that you can reach out to or have the same CC num, then town hall, you can drive whatever streets and you'll come back to town hall. But I was checking that the black box and the output doesn't really return CC num. That's only on BFS. So I'm assuming we cannot use BFS that way, right? To get the CC num.
You have your CC num from the original SCC run, right? So like you have all the information provided to you. So you run your SCC algorithm, and then
Oh, I see. Because you have to run SCC to get the metagraph, and then you'll run BFS. Okay, got it. Thank you.
Yeah, you absolutely need the metagraph regardless of whether you want to look for the sync SCC or you want to run BFS to give you that information.
Yeah, you're right. Thank you very much.
Aaron?
Hey, Joves. Thank you. So my question is more general. I may have missed this earlier, but I understand that the black box algorithms from the DC module in the beginning of the course is still available to us for the rest of the course. And however, I did see that there was a post that says that we're only allowed to use the black box graph algorithms that were given without modifications.
Yeah.
And so my question is, would there ever be a case if we can use, like, let's say, for example, merge sort to try to sort the output vertices or whatever output we get from a black
You
box
can do
algorithm?
whatever you want. You can do whatever you want with the input and the output, however you want to do with it. You can use any other previous taught methods you want. The black box algorithms that we give you are the ones that you cannot modify.
Got it. Okay. Thank you.
All right. Last question, and then I have to go, unfortunately. Mahmoud?
Yeah, so I assumed incorrectly that we didn't have access to the SCC in the previous run. So what I ended up saying was, okay, run BFS from the town hall, and then you'll get a list of nodes that are only reachable from town hall, and then run SSC on that. And that should give you one node if her claim is true, otherwise false if her claim is, sorry, would return false if there's more than one meta vertex. Because I assumed we
Yeah.
didn't have access to the SCC in the previous one.
Yep, that's fine. That's what the other student was suggesting. Run BFS and then run SCC. That's fine. Or you can run SCC and then BFS. Either way is fine.
Would if something like this popped up on the exam and I did that, would that still be considered correct, or would that still be less than efficient and therefore I'd lose
Nope.
points?
BFS is O of n plus m. SCC is O of n plus m. So they would combine to be O of n plus m as long as you get the run times. That would be fine.
Okay, thank you.
Yep. All right, everybody. Sorry about having to cut this a little short. I am being paged, so I have to go figure out what the problem is with my server. But hopefully I covered enough today. Next week, the office hours will be on Monday instead. I am on travel on Sunday, so unfortunately I cannot do office hours on Sunday. It'll be on Monday on Indigenous People Day. I will have a better idea of what that time will be, and then we will post it. I'll try to do it around the evening time because I know some people have to work, unfortunately. I actually have to work that day. I'm taking the day off, so to travel with my family. All right. Enjoy the rest of your weekend, everybody. Thank you.
Good
Thank
luck.
you.
Bye.
Bye.
Thanks, Jovis.